So, what do the semantics are of this, the big step semantics of this OR operator look like? So we have the semantics look like this. We have two rules. We have OR1, which is a big step semantic rule. And that basically says, look, if you have S1 or S2, and you're evaluating it in state S, that's going to go to S prime if S1 in state S goes to S prime. And the OR2 BSS rule says that S1 or S2 in state S evaluates to S prime if S2 in state S evaluates to S prime. So this means that whenever you see an OR expression like this one or this one, you can, well, that's the same one. You have two rules that can apply. So this results in the nondeterminism. So let's evaluate that. Let's look at what the evaluator does with that coin program. So we say like, okay. Coin gets the value of 0, or coin gets the value of 1 in any state S evaluates to, well, if I use the OR1 rule, I get coin, it gets the value of 0 evaluated in state S, and that gives me back, if you go back and look at the big step rules, this rule here says you just take S and you update it so that coin gets whatever the value of that thing is in the A expression semantics. So let me go back to here. So this means that this goes to S, where coin gets the value of 0. And so if we call this thing S prime, then it goes to S prime here. So, but we can also apply the OR2 rule. So coin gets the value of 0, or coin gets the value of 1, comma, S goes to S prime, where coin equals 1 in state S, which evaluates to S, where coin, oh, that's too ugly, coin, sorry, evaluates to 1. And so this is my S prime. So that means that we can evaluate the same program, and non-deterministically it can result in different answers. Maybe I should call this S double prime, because, note that S prime is not equal to S double prime. Why is that? Because remember functions, which remember S's are, these little S's are states, and they're functions because S prime of coin evaluates to 0 and S double prime of coin evaluates to 1. So that shows that these two functions are not the same. Now, this is a different kind of non-determinism than we had in the A expression. Non-determinism. And, in the small steps semantics for A expression. And so let's just look at those for a minute and note that there's non-determinism here because, for example, this rule, maybe I should tag it over here, that rule and that rule, both can be applied. So, for example, I can say 7 times 2 evaluates to 7 times 2 because I can do the mult1 rule here, and I say that, okay, 7 evaluates to 7. And then I can say that, now picking this one up, 7 times 2, well, let's just do this. 7 times 2 evaluates to 7 times 2 because 2 evaluates to 2. So this was the mult2 rule. So I ended up with non-determinism, but we proved a theorem. So there is non-determinism here, but we did that says that the arrow A is kind of eventually non-deterministic. So that meant something like, oh, look, if, what did we say? We said, like, for every A and V1 and V2, if A goes in some number of steps to the value V1 and A goes in some number, 0 or more steps to the value V2, those two things imply that V1 is equal to V2. And so that was our kind of eventually non-deterministic. I'm sorry, I said non-deterministic, eventually deterministic. Because remember that the star operator here is saying 0 or more steps you get to a value. Now, so this is a different kind of non-determinism. because we always get to the same thing. But here we can evaluate this coin flipping program, and we can get to two different answers.